Hello students, in this video we'll see how to write a holomorphic function as an improper integral if the holomorphic function is defined on a right half plane. Let's suppose that f maps the set of points z such that the real part of z are bigger than or equal to gamma, some number gamma, so gamma is a real number here, into c, is holomorphic on the interior of this thing, on the set z such that the real part of z is strictly bigger than gamma, okay? So this, of course, is a right half plane. So let's draw it out. So here's the complex plane. Like that. There's IR, the real axis. And then here's gamma over here. That's the value gamma, okay? Excellent. And so what I'm going to do is now I'm going to pick a point z0 in this right half plane. Okay, which means that z0 is somewhere over here, right? There's z0, okay? And now z0 for r sufficiently large, we have that modulus of z0 is less than r, right? Like that, okay? Just r is in some humongous circle, right? Centered at the origin. Or z0 is in some humongous circle centered at the origin, right? And so pick beta such that what? Such that gamma squared plus beta squared is equal to r squared. That's of course possible because gamma is fixed, right? Gamma is fixed and r is known, right? I can pick a sufficiently large r, so I pick r, then gamma is known. I can find beta by solving this equation, right? Good. And it's important to note over here that as r goes to infinity, so does beta. So note r approaches infinity if and only if beta approaches infinity, okay? That's easy to see because they're just shifts of each other, right? Excellent. And so now what I'm going to do is I'm going to draw that circle over there. So here we go. So we're going to draw that big circle of radius r. So I'm going to put r down over here, then r down over here, negative. Let's draw this big circle of radius r. And of course, where does the circle of radius r intersect this line over here? This point over here is going to be what? That point over here and this point over here. This is going to be the point gamma plus I beta. And then this point over here is going to be gamma minus I beta. Okay? Excellent. And now let me consider the following contour. Consider the contour which is what? Which is the circle in the right half plane and together with the line. To make a closed curve. Okay, so here's my closed curve. Okay, my closed curve looks like this. Like that. And of course, this distance over here is what? This distance is exactly what? R minus z0 right there, okay? Good. Now, here's the key feature. Let's make one more assumption. Here's an essential assumption behind this, and we're going to see why this assumption matters. The assumption is that there exists a k, there is a k bigger than or equal to 1. Maybe it's bigger than or equal to 2. I mean, we'll figure out what the exact value has to be. We can sharpen this estimate if necessary, right? There's a k bigger than or 2 such that modulus of f of z less than or equal to a constant times z to the power k for k sufficiently large, right? For z sufficiently large. Not for all z, but just sufficiently large z, okay? Okay, good, and so that's gonna say, now let's estimate now, so I can apply Cauchy. So by the Cauchy integral formula, implies that, what does it imply that? It implies that f of z0 is 1 over 2 pi I, the integral over this contour over here, call it contour C, right? Over the contour C of f of z over z minus z0 dz, right? And so that's going to be the integral over the circle part. So this is going to be 1 over 2 pi I integral over the circle portion of f of z over z minus z0 dz, like that. Okay, excellent. Alrighty. And so now what? And so now, what's the key thing to note? Plus, I'll put minus actually, minus 1 over 2 pi I, because it's going the opposite direction now. The integral from gamma minus I beta to gamma plus I beta, f of z over z minus z0 dz, right? Good. Now what's going to happen as this r goes to infinity? As r goes to infinity, what's going to happen to this portion of the circle over here, right? What can I estimate this by? I can estimate f of z by r to the power k. This thing in the denominator, z minus z0 is always bigger than what? So note that z minus z0, what can we say about that? So if z is a point on the circle over here, that's the point in z, what can I say about z minus z0? That's bigger than or equal to r minus the modulus of z0 automatically, right? Because I can use the triangle inequality. So the bottom can be flipped, and the bottom looks like a single factor of r. The circle has a what? The circle. So this looks like r. The dz, the length of the circle, looks like r over here. And of course, now we can see that this k has to be bigger than or equal to 1. 2 is even better. So now this thing looks like what? Looks like on the order of what? On the order of r to the power k. And so those r's are going to cancel out down over there. And then these terms over here, I'm sorry, I want this to be a negative k. This has to be a negative k. So that's r to the negative k over there. Excuse me, that's my bad. So it has to be like negative k. Good? So it has to be decaying, right? If it's growing, it's going to be a problem, right? It has to be decaying over there. That's a negative k. Okay? Excellent. And this looks like r to the negative k. So in other words, as that happens over there, what's happening? This integral over here tends to 0 as r goes to infinity, right? So that goes to 0 as r goes to infinity, but as r goes to infinity, this expression over here goes to what? That goes to this limit over here. So we've just proven the following representation formula. We have the representation formula. This implies that f of z0 is equal to negative 1 over 2 pi I, the limit as beta tends to infinity of the integral from beta, from gamma minus I beta to gamma plus I beta of f of z over z minus z0 dz, like this. And this is our Cauchy formula on a what? This is our Cauchy formula represented by a what? By an improper integral. So oftentimes you'll see this in textbooks written as gamma minus I infinity, gamma plus I infinity. That means you're looking at an improper integral where? Over this line over here in the complex plane. And so what I have over here is now I have a single integral over a line representing a holomorphic function in the right half plane under this decay assumption over here. This is a decay assumption. I'm decaying as modulus of z goes to infinity, right? So in that case over here, we're able to represent that holomorphic function in this exact fashion over here. Beautiful. Okay, and so Of course, this is also, this is on a right half plane, so this doesn't contradict anything like Liouville's theorem, because I'm not talking about entire functions. I'm only talking about functions that are defined on a right half plane. Now, the key feature with this is that we want to be able to use this representation over here when we're studying Laplace transforms. What we'll be able to do is I can look at this and I can formally say, oh, if I can represent a Laplace transform in this fashion by an analytic continuation or a holomorphic extension of the Laplace transform, then if I write the Laplace transform in this form, I should be able to do inverse transform by swapping the limits in the Laplace transform, and then get a representation for the inverse Laplace transform as an integral representation with these so-called Bromwich integrals, which we'll discuss in further videos. But this formula over here is the key ingredient behind the Bromwich theory of inverse Laplace transforms, and it's true in a much more, so in other words, this formulation on the right half plane should remind you of the abacus of convergence of the Laplace transform. We always said, for which values of S does the Laplace transform actually make sense? And of course, we're going to take those values of S and extend them to the entire complex plane as long as the real part of S is bigger than the abacus of convergence of the Laplace transform, which is a key feature of how this argument will work in general. Thank you very much.